Hello students, so let us come to the parsing techniques, which are, this is a part of your syllabus in your second unit. So there are various types of parsing techniques, so let us see about that. One is called as a top down and one is called as a bottom up parsing. If you pass a tree right from the top, that means when you can construct from the root and expand it to the leaves, then such type of parsing is called as a top down parsing. And just the opposite of it, when you can construct from the leaves and then you reach the root, then that is called as a bottom up parsing. Now I'll come to these two in a while. So let us see first the type of parsers. Now the parser consists of two types, as I told you, top down parsing and a bottom up parsing. The top down parsing is again split it up into top down parsing with full backtracking and top down parsing without backtracking. And again, top down parsing is without backtracking is divided into recursive descent and non-recursive descent, or sometimes it's called as the LL1 parser. Similarly, in the bottom up, there is an operator precedence, and in LR parser, it's divided into the LR0 or the SLR parser, the CLR parser, and the LALR parser. So let us go about with the top down parsing. Now we should know that parsing is a technique to verify whether your input string is in the correct order or not, or it follows a grammar or not. Now if you consider, suppose, a grammar which is given as S derives X, P, Z, and P derives Y, W, or Y. Now remember, one thing is very important here is the small letters X, Z, Y, W are all terminal statements, and the capital letter S, P, P, they are all non-terminals. Now we can understand non-terminals is they always extend towards the next line. For example, P is here and P is extended in the left side of the grammar. So this is called as a production, one production, this is another production. So S derives X, P, Z, P can be expanded as Y, W, or Y. Now let us see how the top-down parsing works. Now consider an input which is called as XYZ. Now XYZ, first of all, what is there is the input buffer will consider X as the first input. Now when we consider X as the first input, it will consider the first grammar, that is X derive X, P, Z, because X is the first character which appears here. So let us go about it. We'll see that there, if you see the diagram, so you can see that this is a parse tree. We call it as a tree. The topmost is called as the root, and these are called as leaves. So we start from the top, that is S derive X, P, Z. So we have S derives X, P, Z. Now once we find this, then XYZ will match the first character, X will match X. So we have to go to Y. So the second character to match is Y. So you can see that the second character to match is Y. So what we have to do is, we find that P, you see in the grammar, P has two productions, P derives YW and P derives Y. So let us consider that it goes for the YW. So we say P derives YW. So we expand that to P derives YW. Now in such cases, if you match it, if you find X, Y, but the last one is not matching at all, because the leaves has to match X, Y, W, Z. We should get X, Y, W, we should get X, Y, and Z. So it's not matching. So what we have to do is we have to backtrack it. So that's why this arrow is given back. Backtrack it to P again, go back to P, and see in the grammar if there is any other production which is equal, means production of P. So there is another production, that is P derives Y. So we can go for, instead of this, we can go for P derive Y. So now once it is P derive Y, we find that there is a match for Y. So we have X, Y. Then we go for the next one, that is Z. So the tree is sparse. So if the input is xyz, you should get in the tree xyz at the leaves xyz. So this is what is called as top down. We start from the top and gradually proceeds towards the bottom. So the answer is always in the leaves x, y and z. Now look at another example. If we input if the input string is CAD and the grammar is given as S derives CAD, A derives AB, or A, the same thing applies. S derives CAD, A is again, we find that there are two productions of A and B, so it will consider AB. But now we have to match CAD, so CAB is matching here, so there is no answer for that. Go backtracking to A, and then we find there's another production, A derives A, so we get A, so the final answer is CAD, so we get output as CAD. Now the problem with backtracking is, the main problem is it takes so much load in going backwards. So if you see this one, it has to go back. If there's no matching, it has to go back. This is a simple tree. If there's a big tree, then it has to go back one step back every now and then. So we need to move more levels upward in order to check the possibilities. So it increases lots of overhead in implementing of parsing. This is the main problem of top-down parsing with backtracking. Now let us look at another way of using the grammar. Let's understand few things which are very important. One is called as a left recursive grammar. A grammar of the form A derives A alpha. Now alpha can be any, it can be a combination of non-terminals and terminals. That means what? You have a non-terminal, immediately you have a non-terminal, and this plus symbol here, it means one or more step. That means the answer of A can, you have to repeat doing some calculation till you reach A alpha. So it repeats as many number of times. So it is recursive in nature. So if left recursion is there, now let us understand what is left recursion. Let's look at this diagram. A derives A alpha. This A can again deriving A alpha. Again this A can derive A alpha because of the rule A derives A alpha. It can go on repeating this side, this way, and A derives A alpha. If you see this diagram, this grammar here, A derives A alpha. So it will go on repeating this A alpha, A alpha, A alpha infinity times. So it might go into an infinite loop. This is the problem of left recursive grammar. That means what? There is a terminal, a non-terminal, and immediately in the next, in the left side you see there's a non-terminal. Immediately in the right side, just after the derived symbol or the equal symbol, you again have a non-terminal of the same, of A, and it repeats itself, A and A. So in such kind of cases, we have to remove it. So this is what is called as elimination of left recursion. So if you eliminate left recursion, then the grammar will never repeat itself. Like here it is repeating. I mean, the tree will never repeat itself in this case. It might go for infinity. So what we have to do is we have to eliminate it. So to eliminate it is, if a grammar is given by A derives A alpha or beta, so you can see that this grammar is A derives A alpha, so A and A is here. Then we just change the grammar by writing it as A derives beta A dash and A dash derives alpha A dash or epsilon. So it's simply by changing this grammar. That means you take this beta first and make a new symbol A dash, and that A dash will derive alpha A dash, this alpha is taken, and then or epsilon. So this kind of grammar, in such kind of cases, if we change this way, then their left recursion is no longer existing. Now to understand this, let's look at an example. Suppose we have a grammar E derives E plus T or T. Now we can map this with the rule A derives A alpha or beta, such that A is given as E, alpha is given as plus T, because A derives A. This is A again, because A and A is same, plus T is alpha. That's why I told you alpha can be a combination of terminal and non-terminal. So you can see that alpha is a combination of plus is a terminal, T is a non-terminal, and beta is T. So this grammar can be changed as E derive T E dash, E dash derives plus T dash or epsilon. So by looking at this grammar, you can change the grammar to this form. So you can see that E derives E plus T or T has been changed to E derive T E dash derives plus T dash or epsilon. Now a complete left recursion, consider this grammar. This grammar will be frequently using it. E derives E plus T or T, T derives T into F or F derives bracket E or ID. Now let's look at the first grammar. E derives E plus T. You see E here, you see E here. In the second grammar also you see T here and you see T here. So this has to be converted. E derives E plus T is converted as E derives T E dash derives plus T dash or epsilon. So this one line is given in two lines. Now similarly this grammar T derives T into F or F is converted as T derives Ft dash and T dash derives asterisk Ft dash or epsilon. And last one, there is no repetition, F doesn't repeat in the right side, so we'll leave it as it is, F derive E or ID. So this is elimination of left recursion. Now once the grammar is parsed, or I mean to say once the grammar is converted into a left non-recursive grammar, then we can see that if you have a string id plus id into id and you want to find out the solution for it, whether there is a solution or not for id plus id, we just start from the top. So you can see that the grammar will start from E derives T E dash. So we have E derives T E dash, then it goes for from T can be derived as Ft dash. You can see the grammar, you see the grammar, T derives Ft dash, so it just takes Ft dash. F derives id, so you can see from this grammar F derives id. Again immediately go to T dash, T dash derives epsilon, so you can see in this grammar also T dash derives epsilon. Again if you look at the other one, go for E dash. If you go for E dash, what is the grammar in it? E dash derives plus T dash, so E dash derives plus T dash. Again plus is it's a non-terminal, terminal, so leave it as it is. Then you go to T. Now if you look at the grammar T derives Ft dash, so T is derived as Ft dash. Again F is there, look at F derives id because it's a terminal, so F derives id. Then go for T dash. Now T dash derives epsilon, T dash derives epsilon, so T dash will give you epsilon. T dash will give you, there are two productions of T dash. T dash give you asterisk Ft dash, so T dash gives you asterisk Ft dash. Then asterisk is there, which it match the symbol id plus id into, so id plus id into epsilon means empty, remember one thing. So id empty plus id asterisk id, then the last one should be empty, so T dash will derive epsilon. So this gives you the final diagram, id plus id into id. So this is how we use the non-recursive grammar to pass the tree. Now another case of parsing is called as left factoring. Now left factoring is used when it is not clear when two alternatives is used to expand a non-terminal. What I mean to say is, if A derives alpha beta 1 and alpha beta 2, you see alpha is in both cases there, and beta 1 and beta 2. Now I don't know which one should I choose. Should I choose alpha beta 1 or alpha beta 2? Because there are two productions of A. A is alpha beta 1 or alpha beta 2. then what we can do is we break this grammar into this kind of grammar. So a derives alpha a dash, because beta 1 and beta 2 we take as a dash, and a dash can be either beta 1 or beta 2. That means what? First you take this grammar and break it up into 2, and break this beta 1 and beta 2 in a second line. This is what is called as left factoring. Let's consider an example. S is a statement, if else then statement, or if else then statement, else statement. This is an if else statement, or take A. Then this grammar can be broken up as, because you can see is ITS is the same in both cases. IETS. So here there's only one thing is S, and here there's one thing is ES. So what we can do is we can break this grammar as IETS S dash, and S dash can be either a blank or it can be ES. Blank means epsilon or empty we call, or ES, and the other one S can be A or E can be B. So whenever you see a repetition of things and the right side is not sure which one should I pick, then you break it up, what is called as left factoring. Now let us come to the recursive descent parsing. Now a parser that uses a collection of recursive procedure for parsing a given input is called as a recursive descent parsing, or RD parsing. Now in this type of parser, the CFG is used to build the recursive routine. The right hand side auto traction rule is directly converted to a program. For each non-terminal, a separate procedure is written, and body of the procedure is right hand side of the corresponding non-terminal. Now what does this mean is, if you have a grammar, convert it directly into a program. So let us look at the steps. The right hand side is directly converted into programs, code symbol by symbol. So if the input symbol is non-terminal, then a call to the procedure corresponding to the non-terminal is made. If the input symbol is a terminal, then it's matched with the look ahead from the input. The look pointer has to advance on matching of the input symbol. If the production rule has many alternatives, then all those alternatives has to be combined into a single body or procedure. The parsing should be activated by a procedure corresponding to the starting symbol. Now to understand this, let us look at an example. Now let's take this example again. E derives T E dash derives plus T dash or epsilon, T derives Ft dash, T dash derives asterisk Ft dash. Now you see is the starting symbol is E, so the rule says that the parsing should be activated a procedure corresponding to the starting symbol. So we create a procedure for E first of all. So procedure E begin. So in E what do we have is T E dash. So we have T E dash. Now T and E are non-terminals. So if you see in the in the steps, if the input symbol is a non-terminal, then a call to the procedure corresponding to the non-terminal is made. So that is what we have done. So T is a procedure, E dash is a procedure. As you can see, T is a procedure, E dash is not created, but actually it's a procedure. So similarly, it is calling procedure T. Now in T what it has? Ft dash. So you have Ft dash. Again in T dash what it has? It has an asterisk. So if you look at T dash, you can see that if the input symbol is an asterisk, then advance. So what does it say? If you see the rule again, if the input symbol is terminal, then it matches with the look ahead from the input. So if your input is asterisk, then it can go to the next, it can advance forward. So if the input we have inputted is asterisk, then it can advance forward, and then after advancing forward it can go to F, then T dash, Ft dash. Repeat the same process for F. F can be, if the input symbol is an ID, then advance forward. Otherwise, if the input symbol is an open bracket, advance forward. Then go for E. Then go for the closing bracket. If the input symbol is closing bracket, then advance forward. Otherwise, if it's something else, there will be an error. So that means you have a grammar and directly you write a program for it. This is what is called as the recursive descent parsing. So remember, recursive descent parsing is you have a grammar and immediately from the grammar you write a program for it. Now let's look at the advantages and limitations. It is simple to build, can be constructed with the help of the parse-tree. So it is very simple to build a program for it. But the limitations are they are not efficient as compared to other parsing techniques. There are chances that parsing may enter into an infinity loop. Very much chances, huge chances can be there that it can go for an infinity loop. They cannot provide good error messaging. Difficult to parse a string if look ahead symbol is arbitrarily long. So if the look ahead symbol is very long, here you can see that the input symbol or the look ahead symbol is plus, it is fine, but if it is long, this one, then it's very difficult to parse it. So this is the advantages and disadvantages of recursive descent parsing. Now let's look at the predictive parsing. This is again a top-down parsing. So remember, one thing is the top-down parsing consists of the recursive descent parsing, and that is without backtracking. The other one is with backtracking, which I already explained. And now we have another one which is called as the predictive parsing, or sometimes it's called as the LL1 grammar. Now this parsing, what does it do is, the first L stands for input is scanned from left to right. That means you start the input from left to right. For example, predictive P is, we have to search for P first, then R, then E, then D, and then I, and so on. That is from left to the right. The second L means it is leftmost derivation for input string. Now leftmost derivation means, if you see the diagram, let's look at the diagram. It always goes from the left side to the right. T goes to F T dash, then F again, finish everything from the left, then proceed towards the right. That's what is called as a leftmost derivation. Here also you can notice it's written as LM, LM, LM. That is leftmost derivation. And 1 means the look ahead symbol is 1. That means go ahead by only one symbol. That means if P is there, look ahead is R. R is there, look ahead it's E, and so on like that. So that is the look ahead symbol. Now to understand this, first of all we have to understand how do we create it. To create the predictive parsing, we require three things. One is called as the input stack, one is called as the input buffer, one is called as the stack, and one is called as the parsing table. So you can notice in this diagram is the input is here, the stack is here, and the parsing table is here. This is the parsing table, and obviously the program is there so that you get an output whether whatever you have inputted is right or wrong. So input is used to store the input token. So whenever you store an input token, for example A plus B, then we add a dollar at the last to indicate the end of the string. Now stack is used to hold the left sentential form. The symbol in the rule in the right hand side of rule are pushed into the stack in reverse order, that is from left to right. We will understand that in a while. The table has rows of non-terminal and columns of terminal. So you can see that these A, B, C are non-terminals, and A plus B and dollar are terminals. So we call this table as M. So in the table we have to put something. A matches with A. So in this case A matches with A. We have to put something here. We have to put a production. Now two things are very important when you start constructing the predictive parsing table is we have to understand the first and the follow. Now these two things are there, and we have, once we have the first and the follow, then we can always construct the predictive parsing table, and lastly is parse the input with the help of the predictive parsing. These are the 3 steps for construction of a predictive LL1 parser. So let us first of all see what is the first. Computing first function. How do we calculate the first? If A is a terminal, then first of A is equal to A itself. If x derives epsilon is a production, then add epsilon to the first of x. Then same thing, the meaning of this, first of x is equal to epsilon. That's the meaning of that. If x is a non-terminal and x derives A alpha is a production, then add first of x is A. That means if this side is a non-terminal, you can notice x derives A alpha. So A is a terminal. So immediately the first of x will always be the first symbol on the right hand side. And if x is a non-terminal and x produce y1, y2, y3 and so on, so you can notice here non-terminal, immediately it appears with a non-terminal. Then the first of x will always be the first of y, the first of y will always be first of y1, first of y1 will be first of y2 and so on till you reach you get the first non-terminal symbol. Now let's understand this by looking at an example. Now look at the grammar again. E derives E, T E dash, E dash derives plus T dash or epsilon, T derives F T dash, T dash derives asterisk F T dash or epsilon, and F derives E bracket or ID. Let's look at this. E and T. Look at the first line, E and T. E is a non-terminal, T is a non-terminal. So that means what? The first of E will be the first of T. Again, if you go to T down, you can see that T derives F. T derives F. So first of T is first of F. Again, if you go F down, you can see the first of F is the bracket and ID. So the first of F is a bracket and an ID. So that's why you get first of E is first of T is first of F, which is bracket and ID. Similarly, if you see the first of E dash is plus and epsilon, so first of E dash is plus and epsilon. Similarly, if you see the first of T dash is asterisk and epsilon, so first of T dash is asterisk and epsilon. So this way we can always find the first of any function. So it's very simple. If it is a non-terminal, repeat this until you find a terminal statement. So non-terminal, terminal, non-terminal, T, so go for T. T is a non-terminal, F is a non-terminal, go for F. F is a non-terminal and this is a terminal, so first of F is bracket and ID. So obviously first of E is first of T, first of T is first of F, and first of F is a bracket and ID. Now let's look at the follow function. If S is a starting symbol, then follow of S contains dollar. Now dollar is the ending symbol. We consider it as the ending of a string. So if it is a starting symbol, we consider that dollar is completed. If there is a production A derives alpha, B, beta, then everything in first of beta except epsilon is placed in follow of B. If there is a production A derives alpha, B, beta, then first of beta, you notice here is B beta. Remember again one thing, alpha can be a combination of any number of terminals and non-terminals, and beta can also be a combination of any number of terminals and non-terminals. So what we are doing is we are finding the follow of B. So the follow of B is everything in first of beta. So whatever is there in beta will be in follow of B except epsilon. Similarly, if there is a production A derives alpha B or a production A derives alpha B beta where first of beta contains epsilon, so if there is first of beta contains epsilon, then everything follow of A is in follow of B, or follow of B is in follow of A. Now let's understand this. Look at the example. Now E derives T E dash derives plus T E dash or epsilon, t derives ft dash, t dash derives asterisk ft dash, the same grammar we are using. Now let's look at the follow of e first of all. Now let's look at the production f derives bracket e. Now the bracket e, you'll see that after e is the closing bracket. After e is the closing bracket, then immediately the right of e, hence bracket will be in follow of e. The computation rule is a derives alpha b beta. We can map the rule with f derives e, then a is f, then alpha is a bracket, b is e, and beta is bracket. So everything in follow of b is in first of beta. That's the rule. That's the rule says. If there is a production a derives alpha b beta, so alpha is what? Alpha, you can see that it is bracket. Remember, we are finding b, follow of b. So follow of b in this case is follow of e. So the follow of b is the follow of e in this case. So follow of b is first of beta. Anything non-terminal, anything terminal, that is the answer. First beta is a bracket, so it is the closing bracket. So follow of e is a closing bracket. Again, the rule says that if s is the starting symbol, then follow of dollar contains, follow of s contains dollar. So which is the starting symbol? E. So obviously the follow of e will consist of the dollar. So follow of e will consist of two things, the closing bracket and the dollar. Similarly, we can compute the follow of e dash. So let's look at e dash. E dash derives plus t e dash. So if you see, by using this grammar again, you take this e dash plus plus t dash, because we have to find e dash. So there is only one production. This is e dash. You can see e dash derives plus t e dash. Always remember, we are there are two productions. E derives t e dash and e dash derives plus t e dash. Look at the right hand side. Right hand side, there are two productions. One is t e dash and one is plus t e dash. So we have to compute both of them. So if you look at e derives t e dash, remember we have to follow of e dash. So that will be b. So b will be e dash. Then t will be alpha and beta will be epsilon, because there is nothing after e dash, so we'll say it's epsilon. So obviously follow of e dash will be, is because as the rule says, follow of b dash is equal to first of epsilon, first of beta. Follow of e dash is equal to first of epsilon. So this one is the rule. This rule says that if there is a production a derives alpha where first of beta contains epsilon. So if you notice in this case is first of epsilon first of epsilon means in this first of beta contains epsilon. So beta is how much? Beta is epsilon. So first of beta is epsilon. So we have to say follow of a is in follow of b, as the rule says. Follow of a is in follow of b. So follow of a is what? E dash, and follow of b is e dash. Follow of here a dash is e, not e dash. This is wrong. A derives e, so follow of a is e, follow of e, and follow of b is e dash. So follow of e is in follow of e dash. So that's why follow of e is given as closing bracket and dollar. So here also we have closing bracket and dollar. Similarly is the case of e dash derives plus t dash. So you can compute the same way. E dash derives plus t dash. So the same thing can be repeated. A derives alpha b beta. We are finding e dash. So b is e dash, so that is b, and beta is epsilon. So again the same rule applies, because this is epsilon, beta is epsilon, so follow of a is in follow of b. So we get the same answer. Follow of e dash is equal to closing bracket and dollar. Similarly, you can compute a follow of t, follow of f. We can always compute each one of them. Follow of t, follow of f, those can be computed. Now once we have computed the follow of each one of them, so here there's only two computations, e and e dash, but you should also compute the follow of t and the follow of f. That is important. That is left for you to calculate to the same way of as we calculate the follow of e and follow of e dash. You can also calculate the follow of t and t dash. Now once we have done the calculation of follow, so we already got the first of everything, we also got the follow of everything. Then we have to create a predictive parsing table. Now there is a rule which we have to use. So the input is a grammar, the output will be the parsing table. For each production A derives alpha of the grammar, do step 2 and 3. So step 2 and step 3 is repeated. For each terminal A in first of alpha, add A alpha to M A. So for each terminal A in first of alpha, so that means what? In the first of alpha, any terminal is there, you add it directly to MAA. And if epsilon in the first of alpha and A derives alpha to MAB for each terminal B in follow of A, if epsilon is in first of alpha and dollar is in follow of A, then add A alpha to MA dollar. Make each undefined entry to M of M be errors. Now let us look at what this really means. Now we'll understand this is a table, the rule. Now using this rule we'll have to calculate and put it up. So just remember few things are there. Summarization of what we have done. The symbols E, E dash, T, T dash and F. The first is this and the follow is this. This is what we have already calculated. And similarly, first of plus is plus always, first of asterisk is asterisk, first of bracket is bracket, closing bracket is closing bracket, ID is ID and dollar is dollar. So these things are few things we should know first of all. Now once we do that, we have to create the table. Now let's look at the grammar. This same grammar, and this is how the table should look like. We have E, E dash, T, T dash, F, and in the row, means the column section, we have ID plus asterisk, closing bracket, opening bracket, closing bracket and dollar. These are all terminal symbols and these are all non-terminal symbols. Now once that is done, now let us look how we calculate it. Let's look at the first grammar. The first grammar is E derives T dash. Now the first grammar is E derive T dash. We compute it by using A derive alpha, because as per the rule, A derives alpha. Alpha can be anything in it. So let's look at it. A alpha. So alpha, A is E and alpha is plus T. So that means the first of, because as per rule again, for each terminal A in first of alpha, add A alpha to M A and 3. M A and 3. So the first of T dash will be equal to first of T. Now let's look at first of T is what? Where is that? So let us look at this. The first of T is what? A opening bracket and an ID. So let's look at it. The first of T is an opening bracket and an ID. So what you do is, in E of bracket, opening bracket, you put this one, ET dash. In E of opening bracket, you put ET dash. And similarly, in E of ID, you put the same thing. E derives T dash. So that completes the calculation for the first ones. Repeat the same calculation for the second one. Second one means second entry. E dash derives plus T dash. So again let's look at it. E derives plus T dash. A derives alpha. A is E dash. Alpha is plus T dash. So first of plus T dash is first of plus always. So first of plus is always plus. So in E dash plus, we put E dash plus T dash. So in D dash plus, we put E dash plus T dash. Then we have another production, E dash derive epsilon. So again E dash derived epsilon means again the same thing, A E dash alpha, this alpha is epsilon. Now let's look at the rule again. If epsilon is in the first of alpha, so remember this, if epsilon is in the first of alpha, then at A derives alpha to M A B for each terminal B in follow of A. If epsilon is the first of alpha, then and dollar is in follow of A, add A alpha to M A. See the first statement. If epsilon is the first of alpha, then add A alpha to M A B. B is the terminal in follow of A. That means B are all the symbols which are in follow of A. Now let's look at this. First of alpha is epsilon. So what is happening is it says follow of E dash. Let's look at the grammar again. It says follow of A. So A means this A, the starting. You see the starting is A. So that means in this one we're having follow of A. A means E dash. Follow of E dash is how much? A closing bracket and a dollar. Now let's look at that again. If you see follow of E dash is a closing bracket and a dollar. So what we have is E dash and bracket, you store E dash epsilon, E dash and dollar, you store E derives epsilon. Similarly, you can see the computation for T dash and finally F. So you can see that T derives Ft dash. So if you see the same computation is done, then you have T comma bracket, in the bracket, that means the first bracket and ID, you store T derives Ft dash, T derives Ft dash. Repeat the same process for the others. Now similarly we find for F, and similarly we find for ID. Now once that is done, you have created a table, and finally what does the, if you look at the grammar again, point number 4 is make each undefined entry of M be error. So undefined entries means those which are empty. You can notice here there are empty spaces. All these empty spaces can be noted down as errors. So you can say as errors. So this is how we compute the table. So it is very important that you should know how to compute first and follow. Once the first and follow is computed, then immediately you have to know how to put it in a table, and finally mark all the tables with empty spaces as errors. And once that is done, we have finally to prove something or the other by using the parsing table. So if an input string is inputted, we have to see whether that is right or wrong by using the parsing table. Now before we do that, let's look at few actions which are there. If you have a dollar and a dollar in the stack, if you have dollar, now what I mean to say is, let's go back to the beginning. Now you see that in the LL1 parser we have a parsing table, we have a stack. Now this parsing table we have already created just now. The only thing is left is the stack, and we have the program so that we get an output for it. So we have all these things now in hand, ready. Now once these things are ready in hand, then we can start parsing the table. So let's look at it. First of all, if in the stack there's a dollar and the input is dollar, that means we have completed the parsing. We stop it. In the top of the stack is a terminal and the input token is non-terminal. Take out from the stack and advance look into the next token. If in the stack is a terminal and the input is a non-terminal, which is different from the similar, then there's an error. Otherwise, if in the top of the stack there's a non-terminal and the input is a terminal, refer that, and if its entry is MA is error, otherwise error is reported. And if AA, another case, if entry at MA is correct, then take out from the stack and push R and Q, then push P on the stack. So that means what? You go from the reverse, R, Q, P. So we push R, Q and P into the stack in the reverse format. Now to understand this, let's look at an example for it. Now look at this diagram which we have created, and let's prove ID plus ID asterisk ID dollar, whether it is right or wrong. So what we do is we start with the first one. We put in the starting symbol E in the stack, and we take this input symbol as ID plus ID into ID asterisk. Now if you look at E, you see E with ID, E with ID. So this E with ID matches E derives TE dash. So what we do is we remove E from the stack and push in E dash T. So we push in E dash T. So you see that we have push it in the reverse form. Here it was T dash, we put it as E dash T. Then again you take T with ID. Look at the table, T with ID, you get FT dash. So what you do is you take out T from the stack and then put F T dash in the reverse order there. Again you take F with ID. You see F with ID, where is the match? F with ID is ID. So we remove F from the stack and put ID in it. And if there's a match ID with ID, you remove both the things from the stack. That means what? We have matched the first character ID. So ID is removed. Again it exposes T dash and it exposes plus. So you see T dash with plus. So T dash with plus, what it is? Epsilon. So T dash with plus is epsilon. So don't do anything, just take out, because epsilon we cannot write here, so we are not writing, we are exposing E dash. Again we take E dash with plus. So if let's look at it, E dash with plus is what? E dash with plus, it is plus T dash. So plus T dash. So we take out E dash from there, we keep plus T dash. Again plus and plus, there is a match, so we remove it. So we have matched the plus, the second plus. That's the meaning of that. Repeat this process. T with ID. T with ID gives you FT dash. So we put T dash F. So T dash F. Again F with ID, there's a match, that is ID, so put ID and ID. There's a match ID and ID, so ID is removed. That means what? The symbol ID plus ID is done, finish. Then we have T dash with asterisk. So T dash with asterisk, it gives you T dash derives FT dash. So that is asterisk FT dash. So asterisk and asterisk is exposed, so it is matching. So take it out, you have F with ID. So F with ID gives you ID itself. So that is ID itself. ID with ID, there's a match, so it's taken out. So there is exposing T dash with dollar. So if you look, T dash with dollar, it exposes epsilon, so it's just removed. Then it exposes E dash with dollar. So if you see E dash with dollar, it is epsilon, so it is removed. Then we get dollar and dollar. So as the rule says that if you have dollar and dollar, parsing successfully halted. So that means we have proved that ID plus ID into ID is correct, what we have inputted. So this is how we use a predictive parsing. So that completes the chapter of predictive parsing table. Now remember one thing is there, predictive parsings, all predictive parsings are not not all grammars are predictive parsing grammars, or they are not LL1 grammars. Now how do we know that? Now here is an example for that. Now consider the grammar S derives ITS, if else then statement, if else then statement, else statement. Now once we eliminate, use left factoring for it, we get this, and once you calculate the first and follow of it, we get this. Now let's look at the table. The same way we put in the table how it is put before. So S, in S we put SA, here we put SIETS, SS dash. It's the same way as we have followed in the previous example. But if you notice in S dash, in C, there are two entries. S derives ES and S dash derives epsilon. Now if you see two entries like this, then this is not an LL1 grammar. So we cannot use LL1 for such kind of grammars. Generally LL1 grammar will never have any two entries. If you notice this table here also, there is only one entry for one cell, but here in this case there is one entry, two entries for one cell. So such kind of grammars are not LL1. So if a question arises that are all grammars LL1, then the answer is no. So that completes your chapter on predictive parsing or LL1 grammar.